Hi everyone, welcome back. This video is the first in a series of videos to cover the entire process that we follow in our laboratory to go from new research idea, to collecting the rocks, to collecting the data, to analyzing the data, and to finally sharing our results with the scientific community at large. First, we need to answer our hypothesis. In my case, as a paleomagnetist, my questions focus on characterizing the behavior of the magnetic field throughout Earth's history. Let's try to come up with a hypothesis that we can answer over the next few videos. Creating a scientific hypothesis has a few requirements. The most important one is a fundamental point for science. A scientific statement is one that can be disproved. Keeping that in mind, we can start coming up with some potential questions about the Earth's magnetic field. Since we already know from the last video that the magnetic field changes over time, we could ask, for example, would compasses have pointed north or south 10 million years ago? Maybe we're more interested in plate tectonics and want to know, where was this continent 100 million years ago? Perhaps we care about what's going on in the Earth's core, where the field is generated. Then we can ask, how strong was the magnetic field 400 million years ago? These are all great questions. If you have your own idea for a question, leave a comment down below. Now that we have some questions to ask, let's go about finding out how to answer them. The best way we have to answer all these questions is actually all around us. Rocks. The entire Earth is covered in rocks, so there's a lot of choice for where we want to investigate. Inside of most rocks exist small grains of magnetic mineral, which is aptly named magnetite. Magnetite grains are themselves magnetic. If you were to get a lump of magnetite, it would stick to metal like any other magnet, which is pretty cool. However, most rocks have only small grains of magnetite in them and are therefore not very magnetic. It's not a problem for us though, because specialized equipment in laboratories can still measure changes in the magnetism of rocks that contain magnetite. When a rock forms, for example after a volcanic eruption, these magnetite grains align themselves to the local magnetic field. Their direction is therefore parallel to the Earth's magnetic field, and the strength of the magnetic field of the rock is proportional to the strength of the Earth's magnetic field at the time. This is an important result because it means that we can use the data from volcanic rocks to determine both the direction and the strength of the magnetic field any time in the past, as long as we can find a volcano from that time period. Luckily, the Earth has a lot of volcanoes. The first step in our process is to pick somewhere to go. And once we pick that, we then will look to see where others have gone before us, because first, it stops you from accidentally duplicating a good study that has already done what you want to do. But more importantly, it means your experiments will have a higher chance of success because you have some idea of what to expect when you're there. I was told once, 6 hours in a library can save you 6 months in the laboratory. In our case, there are a lot of reasons that one might be studying the Earth's magnetic field, and the data required to answer different questions can be quite different. So it's rarely a waste to go back for more paleomagnetism data. It's also easier to convince someone to pay for your trip when you can show that you'll definitely be getting some good data. Geologic maps exist for most of the world, as geologists have been wandering the world for new rocks to study for hundreds of years. If a previous study isn't available immediately, or you want to go somewhere completely new, these maps are the main place we can go to find new rocks. What's even cooler is that a lot of these maps are now available as Google Earth files, so they can be directly overlain with the GPS coordinate. So if you're out in the field, you always know what rocks you're on top of.